One of the last things we want to be able to do in terms of using trigonometric functions is to be able to solve certain trig equations. For example, if we look at example number 4 in the notes, we want to solve the equation the sine of theta equals to the negative square root of 3 over 2. We know that trig functions are periodic, so odds are if we have one solution, there's going to be infinitely many, and that's what we want to be able to find. We want to find all solutions, in other words, all values of the angle theta, for which this equation is going to be true. In order to find those angles theta, it's again helpful to kind of know what to look for. First of all, we have the sine of theta is equal to a negative value. From our all students take calculus, the only potential places where the sine of theta could be negative would be in quadrants 3 and quadrant 4, right? Because in quadrants 1 and quadrants 2, the sign is positive. So for the sign to be negative, we're talking about an angle theta that would either have to lie in quadrant 3 or quadrant 4. Thinking about the actual value, so if I'm thinking about just not the negative square root of 3 over 2, but the value square root of 3 over 2, we know that the sine of, let's say, pi over 3 would be equal to the square root of 3 over 2. So the reference angle, the acute reference angle that we're dealing with here, in order to get a sine whose value in magnitude is radical 3 over 2, that reference angle would have to be pi over 3. We can work backwards then to find the solution in quadrant 3. If you recall, the way that a third quadrant reference angle is found is by taking theta and subtracting pi. Well, we know the reference angle would be pi over 3, and this gives us an equation where we can solve for the third quadrant angle theta. To get the theta by itself, all you would have to simply do is add pi to both sides. So add pi, and we get, after getting a common denominator, pi over 3 plus pi is going to be equal to 4 pi over 3. So one solution that's going to work is going to be the third quadrant angle pi over 3. There should also, as we mentioned a moment ago, be another angle that's going to be in quadrant 4. The reference angle in quadrant 4 is found by doing 2 pi minus theta. The acute reference angle is that pi over 3. And this will allow us to solve for that fourth quadrant angle theta. To get theta by itself, we would first begin by subtracting 2 pi from both sides. This would say that pi over 3 minus 2 pi, get common denominators and all that good stuff. That should give us a value of negative 5 pi over 3 is equal to negative theta. And then to get theta by itself, simply divide both sides by negative 1. And that would give us that theta equals 5 pi over 3. So the two angles we found were theta equals 4 pi over 3 and theta equals 5 pi over 3. But these are not the only ones. Obviously, any angle that's coterminal to those two would have the same trigonometric value and therefore would also be a solution. Therefore, all of the solutions would be given by 4 pi over 3 plus 2 pi n, where n is any integer. And similarly, 5 pi over 3 plus 2 pi n, where n is any integer. So this would be all of the solutions to the equation, the sine of theta equals negative square root of 3 over 2. Let's take a look at the next equation. In example 5, we're asked to find all of the solutions to the cosine of 2 theta equals 2 minus this 3 sine theta. Okay. In order to solve an equation like this, so typically, anytime you have, let's say, like a function, so a second power, excuse me, or even like a double angle, it might be helpful to use a trigonometric identity. And here, we definitely wanted to kind of do that. What we kind of have is a mixture of cosines and sines. And then furthermore, in addition to that, we have not just a single angle theta on the inside here, we actually have a 2 theta. It would be helpful if we could somehow eliminate the double angle, the 2 theta, and end up with just like a single angle here. And if you go back to the identity sheet, there's actually 3 different formulas for the cosine of 2 theta. The one that we would want to use in this case that would be the most helpful to us would be the following. We have the identity that the cosine of 2 theta is equal to 1 minus 2 sine squared theta. And the reason for the choice of this identity, as opposed to some of the other options for the cosine of 2 theta, is that this would leave us with an equation that only would involve the sine function, which is going to be an advantage later on. So what I'm going to do is everywhere we see the cosine of 2 theta, we're going to replace it with 1 minus 2 sine squared theta. So under that substitution, our equation now becomes 1 minus 2 sine squared theta is equal to 2 minus 3 sine theta. So far so good. We now at least have it down to just all functions where the angle is just theta. And in addition to that, all of the trig functions are in terms of the sine function. To solve it from here, we notice that it's actually it's actually a quadratic equation in the variable sine theta. So we're going to bring all of the terms to one side and set one side equal to 0. In order to do that, it's probably best, let's make the left-hand side 0. I'm going to subtract 1 from both sides. And in addition, I'm also going to add 2 sine squared theta to both sides. If we do this, the left-hand side is going to be 0. And we get that this is going to be equal to, writing it in standard form, we're going to have a 2 sine squared theta minus 3 sine of theta. Positive 2 minus 1 would give us positive 1. And we have this quadratic equation in the variable sine theta. To solve a quadratic, we would try to factor it, and luckily this one will factor. This will factor as 2 times the sine of theta minus 1 times the sine of theta minus 1. Once we have it factored, we now would set each factor equal to 0. So we have 2 times the sine of theta minus 1 equals to 0. The sine of theta minus 1 equals to 0. And then solve each equation independently. For this one here, we would add 1 to both sides. This would say that 2 sine of theta equals to 1, or that the sine of theta equals to a half. In order to solve this little mini equation, again, kind of use the same logic that we used in the previous example. The sine of theta is equal to a half from our all students take calculus. The sign is going to be positive in both quadrants 1 and quadrants 2. So there should be a first and second quadrant solution to this equation. In quadrant 1, this is one we should know right off the bat from our unit circle. One answer is going to be pi over 6. The solution in quadrant 2, again using reference angles kind of working backwards, you should be able to solve for this and you would get 5 pi over 6. Because they're asking for all solutions, not just the solutions between 0 to 2 pi, we have to realize that also any integer multiple of 2 pi added to those values would give us a coterminal angle, which would also be a solution. So any angle of the form pi over 6 plus 2 pi n will be a solution to our original equation. And similarly, any angle theta of the form 5 pi over 6 plus 2 pi n will also be a solution to the original equation. We also have to solve that secondary equation that we came up with. The sine of theta minus 1 equals 0. We simply add 1 to both sides, and we get that the sine of theta would be equal to 1. The sine of theta is going to be equal to 1 precisely when the angle is pi over 2, because this is the point on the unit circle 0, 1. So the angle theta that works here is going to be pi over 2 plus 2 pi n, any angle that would be coterminal to 2 pi n.